Imagine you are having 3 pencils of different lengths like 15 cm, 10 cm and 4 cm and try to break each of them. It would be easy to break the 15 cm pencil, right? For the pencil with 4 cm length, we need to provide more energy to break it. Likewise, a bond with large bond length is easy to break than those with shorter bond length. We will discuss similar bond parameters in this video. So, bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. For a molecule AB, the bond length would be the sum of radius RA and RB. In case of covalent bonds, the contribution from each atom is called covalent radius. We know that covalent bond is formed by the overlapping of orbitals. For this type of bonded atom, the radius has to be defined as covalent radii. The covalent radius is measured approximately as the radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. Here, atom's core represents the center of the nucleus. That is, the covalent radius is half of the distance between the two similar atoms joined by a covalent bond in the same molecule, as you can see here. In the case of unbonded atoms like helium, neon, etc., the bond length is measured using van der Waals radius. Now, what exactly is van der Waals radius? Well, van der Waals radius represents the overall size of an atom, which includes its valence shell in a non-bonded situation. The van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. So, as we know that these atoms and molecules are extremely small and it is impossible to see them directly, then how can we measure this bond length? For this purpose, we can use spectroscopic, X-ray diffraction and electron diffraction techniques. We can see different bond length for different bond type and molecules, such as OH bond length is 96 picometer and CH bond length is 107 picometer. The bond lengths of carbon single bond, double bond and triple bond are 154, 133 and 120 picometers respectively. This indicates that the bond length decreases with increasing the number of bonds. Bond angle is the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion, and it is expressed in degree. For example, consider water molecule. The angle between the two bonds of water molecule is equal to 104.5 degree. This gives us some idea regarding the distribution of the orbitals around the central atom in a molecule or complex ion. So, it is helpful in determining the shape of the compound. Enthalpy generally means measurement of energy in a thermodynamic system. So, bond enthalpy means the amount of energy required to break 1 mole of bonds of a particular type between two atoms in the gaseous state. The unit of bond enthalpy is kilojoule per mole. Let us see few examples to find the bond enthalpy of diatomic molecules. Diatomic molecules have two atoms and that is broken into two single atoms. Consider a hydrogen molecule that is in gaseous state. The energy required to break this hydrogen-hydrogen bond is 435.8 kilojoule per mole. We should remember that to break the bond, the molecules must be in gaseous state. If it is in solid and liquid state, first we should convert it into gaseous state for breaking the bond. Now, to break the double bond in oxygen molecule into two single oxygen atoms, the energy required is 498 kilojoule per mole. This shows that energy required to break double bond is higher than that of single bond. Suppose if you take nitrogen molecule which has a triple bond between nitrogen atoms, the energy required to break this triple bond into two single nitrogen atoms is 946 kilojoule per mole. By comparing all these energies, we understand that the energy required to break the triple bond is very high and the energy required to break the single bond is quite low. Next, let us check the bond enthalpy of polyatomic molecules. As the name suggests, polyatomic molecules have two or more atoms. For example, consider a water molecule with 3 atoms. It has two OH bonds as you can see here. Here, breaking of water molecules takes place in 2 steps. First, the hydrogen bond is separated and the energy required to break this water molecule is 502 kilojoules per mole. Secondly, the OH group is broken into O and H separately. Now the energy required for this process is 427 kilojoules per mole. After this, we need to find bond enthalpy for this total process. There are some differences in the bond enthalpies of two OH bonds. This is because the second OH bond undergoes some change due to the changed chemical environment. So in polyatomic molecules, we need to calculate as average bond enthalpy or mean bond enthalpy. It is obtained by dividing the total bond dissociation enthalpy by the number of bonds broken. That is, average bond enthalpy of water will be equal to 502 plus 427 divided by 2, which will give 464.5 kilojoules per mole. Now let's discuss about bond order. Bond order is given by the number of bonds between the two atoms in a molecule. As you can see in this table, the bond order between hydrogen molecule, oxygen molecules and nitrogen molecules are 1, 2 and 3 respectively. This is because in the case of hydrogen molecules you have 1 electron pair shared, and in the case of oxygen molecules there are 2 electron pairs, and in the case of nitrogen 3 electron pairs are shared. But in case of isoelectronic species, which means they have the same number of electrons, they have identical bond orders. For example, F2 and O2 2- have the same bond order, which is equal to 1. N2, CO and NO plus have the bond order of 3. Also note that bond enthalpy increases with increase in bond order and bond length decreases with increase in bond order. Now look at the Lewis dot structure for ozone. The structure is represented in two ways. In both the structures, we have an oxygen-oxygen single bond and oxygen-oxygen double bond with bond lengths 148 and 121 picometers respectively, as you can see here. Experimentally, neither structure 1 nor structure 2 is correct, and it is represented by a third structure called a resonance hybrid. Here, we can notice the bond length is 128 picometer in both the cases, and both the bonds are also found in between single and double bond, as you can see here. When more than one structure with similar energy, position of nuclei, bonding and non-bonding electron pairs are possible, these structures are known as resonating structures of the molecule. Here, Lewis dot structure 1 and 2 are called canonical structures. These structures do not completely explain an accurate structure of the molecule, so the concept of resonance exists. Like ozone, carbonate ion and carbon dioxide molecules also have resonance hybrid structures. It is stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. Also, resonance averages the bond characteristics as a whole. Well, there are some misconceptions associated with canonical forms, such as the molecule does not exist for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. There is no such equilibrium between the canonical forms. Lewis structure has more than one possible structure for a molecule, but resonance hybrid has single structure for a molecule. We have discussed about different parameters till now. With this understanding, can you predict the bond angle of methane and carbon dioxide? With this, I will summarize this video.
Manorama Horizon. Learning made simple.